I welcome you to the webinar about versatile options with evolved gas analysis. My name is Caroline Fischer. I'm working since 2011 for NETZSCH Analyzing and Testing as application specialist for hyphenation techniques. Temperature treatment of different materials can release gases. Different processes can occur, like outgassing of inclusions, decomposition, or evaporation. Thermoanalysis in combination with evolved gases analysis is the right tool to get a deep insight into these processes. The sample is subjected to a controlled temperature program. The evolved gases are immediately transferred over a heated interface to an evolved gas analyzer. NETZSCH offers a great variety of different gas analyzers in combination with thermal balances or simultaneous thermal analyzers. These are in principles: on the upper left side, the couplings to FT-IR spectrometer. On the upper right side, the coupling to MS spectrometer. Or down on the middle, the coupling to TGA-MS systems. Today, I will discuss a few questions you may get in contact during your daily work and how they can be solved by evolved gas analysis. Question number 1. How to identify plasticizer in PVC? Question 2. Is the identification of a blend composition possible? Question 3. How can the thermal decomposition of salts be monitored? Question 4. How can a redox process be monitored? Question 5. Does thermal treatment lead to evaporation or decomposition of pharmaceutical excipients? And last question for today: how to distinguish tiny differences in natural products. So we directly start with question number 1. How to identify plasticizer in PVC? One of the most known group of plasticizer is the group of phthalates. DEHP is one important member of this group. Western Europe produces 1 million tons of phthalates per year. 90% thereof are dedicated to production of plasticized PVC. Phthalates are chemically not fixed and can be washed off. Almost every person has detectable amounts of phthalates inside blood or urine. According to EU risk estimation, phthalates are toxic for reproduction. So with the REACH regulation from January 2015, phthalates are no longer allowed to be used in food, in toys, in baby articles, or medical supplies. The outgassing of a plasticizer during thermal treatment can be easily monitored by infrared spectroscopy. Infrared spectroscopy exploits the fact that molecules absorb frequencies that are characteristic for their structure. So let me briefly discuss advantages and limitations of this method. The absorption spectrum shows functional groups and inorganic gases. With the help of libraries, the interpretation and identification is rather easy. Even the detection of CO is possible also if nitrogen is used as a purge gas, in contrast to mass spectrometry, where this is not possible. On the other hand, homonuclear molecules and noble gases cannot be detected. Compared to mass spectrometry, the FT-IR technique has a smaller linear range and lower sensitivity. The detection limit is between 10 and 100 ppm. NETZSCH can offer two different solutions for FT-IR coupling. On the left, the direct coupling, the so-called Perseus coupling. This is the case when the Bruker alpha spectrometer sits directly on top of the gas outlet of the furnace and is connected by a short and heated steel tubing. This is a very space-saving and cost-effective version. However, the coupling can also be realized to the high-performance Bruker in vivo instrument over a heated transfer line and the connection to the external gas cell of the in vivo instrument. You see here on the right. So let's come to the investigation of plasticized polymer. Here we now see the thermogram of plasticized PVC. Two mass loss steps of 74 and 16% were detected, with peaks in the DDG curve in green at 312 degrees C and 467 degrees C. The Gram-Schmidt curve in blue displays the overall IR intensities and acts as a mirror image of the DDG curve. This proves the interaction of the gases released with the IR beam. The three-dimensional plot shows all IR spectra in correlation to the temperature and the TG curve in red. However, every single spectrum can be extracted. Now the spectrum at maximum intensity for the first mass loss step at 318 degrees C is taken and compared to the gas phase library. The single spectrum at 318 degrees C is displayed in red. Library search gave high similarity to DEHP, the blue spectrum, and hydrogen chloride, the green spectrum. Thus, it can be concluded that during the first mass loss step, the plasticizer DEHP was released from PVC, and PVC was already decomposed. Please let me mention that a non-plasticized PVC would only release HCl during this first mass loss step. So this leads me directly to question number 2. Is the identification of a blend composition possible? Also, this question can be solved with help of TGA-FT-IR coupling. This plot depicts a measurement of a blend consisting of more than one compound. However, the TG curve exhibited only one mass loss step of 98%. The Gram-Schmidt curve shows again the release of IR-active gases. From this graph, we would not expect more than one compound. The 2D spectrum at 456 degrees in red was extracted and compared to the NETZSCH database of polymers. This database consists of pyrolysis spectra of all common polymer classes. This comparison gave some unique vibration bands typical for PA6 in the wave number range between 1400 and 1700 reciproc centimeters, which are marked with red cycles. Additionally, significant similarity was found to ABS at 2 points of the spectrum. You see with the green circles. So it can be concluded that this blend consists of PA6 and ABS. As a side remark, it has to be mentioned that this identification over TGA-FT-IR gets a little more difficult if pyrolysis spectra of the single compounds are rather similar. The coupling of thermoanalysis and infrared spectroscopy can also help to solve other problems, as pyrolysis studies of biomass samples, thermal stabilities of polymers and pharmaceuticals, failure analysis of polymers, decomposition reactions of minerals, and others more. So let's come to the third question from the field of inorganics. How can the thermal decomposition of salts be monitored? Salts can be divided into different classes. This can be halogen salts, carbonates, sulfates, nitrates, phosphates, and others. Some of them can build hydrates, and thermal decomposition may cause the release of gases like water, carbon dioxide, sulfur dioxide, NOx, or ammonia. The detection of permanent gases is an easy task for mass spectrometry. Mass spectrometry is an analytical technique that ionizes chemical species and sorts the ions based on their mass-to-charge ratio. The advantage of this method is the fast scanning rate and the high sensitivity. The high linearity enables quantification studies over several decades. On the other hand, the fragmentation, especially of simultaneously released organic compounds, complicates the identification. Also for mass spectrometer coupling, NETZSCH offers different solutions. On the left, you can see the coupling over the capillary made from silicon to the aeolus quattro. The pressure reduction to the mass spectrometer is realized over this capillary. On the right, you see the direct coupling, the so-called skimmer coupling. The pressure reduction to the MS, which sits directly on top of the furnace, is realized over a two-step orifice system. The aeolus quattro on the left is used to detect permanent gases and small organic fragments. The skimmer on the right takes advantage that the MS is nearly working at sample temperature and can be therefore used for high boiling materials like metal vapors or long-chain hydrocarbons. The measurement of neodymium sulfate with an STA coupled to the aeolus quattro exhibits three mass loss steps of 13%, 24%, and 12%. Scanning the complete mass range from 1 to 500 AMU gave an increase in mass numbers 18 in blue, 32 in red, and 64 in purple. Mass number 18 shows the release of water during the first mass loss step. During the second and third mass loss step, the decomposition of the sulfate can be proven as oxygen and sulfur dioxide with mass number 32 and 64 were released. So you see that the aeolus quattro can easily detect the decomposition of salts. Also question number 4, how can a redox process be monitored? Comes from the field of inorganics. And this is also a suitable task for TGA-MS coupling. Here we see a reduction in oxidation study of a perovskite sample. The sample was heated to 650 degrees C, and then the temperature was kept constant. Then the purge gas atmosphere was changed from hydrogen to oxygen over several cycles. The result was a reversing mass loss and mass increase for each cycle. Here we see that the applied gas atmosphere, hydrogen and oxygen, can be detected by the traces of number 2 and number 32 by the MS. And we see that, for example, the hydrogen was completely purged out before the oxygen was applied. Additionally, the creation of water could be detected for every reduction step. As soon as hydrogen was applied, oxygen was released, which resulted in the release of water with mass number 18, you see in the blue curve. And this blue curve is then in good relation with every mass loss detected. Besides these examples of salt decomposition and redox study, also other questions can be solved with mass spectrometer coupling. The binder burnout of ceramic green bodies, quantification of released gases, detection of high boiling materials like heavy oil fragments, salts or metal vapors by the skimmer system, or the tracking of reactions in humid atmosphere. The fifth question leads us to the field of pharmaceutical applications. Very interesting for formulation or storage is the question, does thermal treatment lead to evaporation or decomposition of pharmaceutical excipients? The analyzing of demanding gas mixtures from the field of organics and pharmaceuticals is the TGA-CG-MS coupling is the appropriate solution. GC is an analytical technique that separates gas mixtures due to their different chemical and physical interactions with a column filling the stationary phase. You see here on this small animation that the different colored dots are moving in a different speed over this column, and this depends on their chemical structure, on their size, on their polarity, and other parameters. The advantages of this method is the separation of complex mixtures by the GC column, which facilitates the interpretation of released gases. The cryotrap option enables a very high sensitivity. As limitations, it has to be mentioned that no continuous traces can be detected for each molecule, as the separation over the column takes some time, and the sampling is realized over a valve system. The coupling system consists of the thermal analyzer, which can be a TG or an STA, shown on the right, the heated transfer line, this is the black tubing, the heated valve box, which is this silver box with NETZSCH on it, the gas chromatograph, and then the mass spectrometer on the left. To avoid condensation in the interface, it is absolutely necessary that all transfer parts are heated. The valve box consists of a heated loop which is filled with a sample gas in blue, and this is then by valve switching injected onto the column. A carrier gas or mobile phase is used to inject this gas. The optional dual loop arrangement increases the injection time by 100%. On the left, you see the structure of the common sweetener and pharmaceutical excipient aspartame. The question is now, which process occurs upon heating, evaporation or decomposition? The TG curve gives 3 mass loss steps of 0.2%, 15% and 66%. For detailed analysis of evolved compounds, the gas portions of each mass loss step was injected onto the GC column. This was the so-called event mode. On this slide, the resulting total ion chromatogram is depicted. The first mass loss step showed only one peak in the chromatogram. The comparison of the measured MS spectrum for this peak with the library gives the release of water. So up to 150 degrees C, the original molecule was not decomposed, only moisture was released. For the second mass loss step, also only one peak was detected. Here, methanol was identified. This can be easily explained by the cleavage of the ester functionality we find on the molecule. During the third mass loss step, the chromatogram shows several peaks, and library search could identify several compounds, like phenol and others more, CO2 and complex organic fragments. So it is obvious that aspartame was pyrolyzed into several fragments. So it can be concluded that a decomposition and not an evaporation takes place during heating. One question which comes from the field of natural product research is how to distinguish tiny differences in natural products. This example here we can see two different tobacco samples. The two thermograms both show 4 mass loss steps. A significant difference could be detected for the first mass loss step, which was probably due to the different moisture content. Also, the other mass loss steps show minor differences. However, the single TGA measurement cannot clarify if there are really occurring different processes during heat thermal treatment. Here we take the advantage of the GC-MS cryotrap method. The released gases were sampled in short intervals on the cryotrap at -50 degrees C and condensed there. Only after the end of the TG measurement, the cryotrap is heated and the evolved gases were separated on the GC column. This procedure increases the sensitivity of minor products and improves the separation. By comparing the resulting total ion chromatograms, it was possible for these two tobacco samples to identify 2 pyrolysis compounds, which were individual for each of these samples. So in the blue ion chromatogram, we only find propylene glycol, which was not present in the other sample. And the same was right for this aldehyde compound, which we only found in this green ion chromatogram. In principle, such studies can also be possible for other natural products like soil, biomass, and others more. In addition to these examples, GC-MS can help for studies of evolved gases during long-term annealing or storage, identification of flame retardant or plasticizer, and failure analysis. At the end, I will summarize which of the method is suitable for which kind of material. Here you see different material classes. They are sorted from complex matrix to few compounds which will probably released during heating. If we take a look on FT-IR technique, it is mainly used for analysis of released gases from organics, polymers, adhesives, and in some cases for inorganics. If the task is to detect permanent gases or small organic fragments, the MS-IR system is the right instrument. For high boiling salts, metals, or organics with high boiling points, the skimmer system is the right system. Finally, GC-MS enables the separation of complex mixtures which appear during the decomposition of biomass, organics, pharmaceuticals, or polymers. In summary, evolved gas analysis gets increasingly important for advanced analysis of thermal analysis. A broad range of different systems like FT-IR, MS, GC-MS is available, which can be connected directly or via a transfer line to a thermal analyzer instrument. The results presented could demonstrate the various applications possible and the advanced output of current evolved gas analysis systems. At the end, I would like to thank you for your attention, and please feel free to submit your questions.